Thank you very much. My name is Ianu Kim from Mercury, and my talk is, kind of a grand title, like a Towards Dream Haskell Build Experience. This is basically our status report about how we scaled Haskell with the Buck2 new build system from the Meta. So who are we actually? It's not just Mercury, in fact. So we have kind of formed quite a large kind of a collaboration group with Twig and Well-type. So we call it Mercury GHC build collaborations. So we have worked together last 3 years, more than 3 years actually. And this is basically our backend developer experience team plus this Twig and Well-type, and including the Matthew, Rodrigo, and also Chang in here. Yeah. So in this group, you have 10 to 12, depending on the situation. We actually have some around the 10 engineers and who are GHC experts and also build system experts. So this is actually a very good chance for us to start some kind of very somewhat ambitious goal with this very expert people. So we previously actually focused on the mainly GHC build performance and the memory usage, but we found that we have to focus on really how to scale the Haskell with the modern build system since last year. And especially this must be guided from the very first principles. So to give you a context, the Mercury is actually the kind of startup company which provides the banking service to startups actually. Then we are actually growing quite fast right now. And our code base is almost entirely the Haskell in backend. It's already the 1.5 million source lines of code, and with the 14,000 modules, and with more than 250 engineers. So it's a very, kind of a unique situation in Haskell ecosystem, in fact. And also, our code is a little bit unique because it has a very template Haskell-heavy code base, which is based on the basically YESOD and then persistent stack, which usually makes the code base more template Haskell oriented. So about 50% of this 14,000 modules are actually using template Haskell, and also it has a very large dependency footprint over the 600 external Haskell packages that we depend on. And we actually use a fairly up-to-date GHC 9.10, and also we have been using the Kabar until recently. But as you know, as a developer, so when developer complains about the build, then that's usually from the two sources, right? The one is basically it's too slow. My iteration cycle for development is too slow, and I have some minimal changes, but the CI just triggers a whole build, and it takes 25 minutes, and also deployment takes more than 1 hour, kind of things. So we actually hear a lot as a backend developer experience team. We hear a lot of these complaints these days. And another source is, of course, also the integration inconsistency. As your system grows, your system has lots of layers, and then layer by layer, it has a very different methodologies used, and then often whenever you have to explore another layer, then you have to change your whole methodology a lot, and then that's really pain. So developers really dislike this thing. And then, of course, as we scale up, this problem became more and more acute, and more frequent contributions, and more conflict, and more rebuilds from the dependency changes. And the sheer volume of the computation is really big right now. And big build latency is really unbearable. And also, as you know, the diverse development task now arises, back-end, front-end, mobile, data science, design, and documentation everywhere. So we explored what is the possibilities, and then we would like to just explore the modern build system, how other big, large companies does. Of course, Google and then Meta all have these solutions, or experience the same problem and then solutions. And Google, comes out with this open source project Bazel, and Meta has also very similar project Buck, and recently they announced the Buck2 since 2023. So all this kind of this modern build system is based on the very important 3 principles actually. So first of all, since they are large organization, they have to support all kind of languages, and the build system must be very language agnostic, and then also all kind of the build rules are very unified way, and very homogeneous and unified way. So the build system must be unified in polyglot oriented system. And more importantly, actually, the build must support the very incremental build. So that means basically you have, whenever you have some the build up to a certain point, then that point is just checkpointed, and then the later build just based on that. So incremental build, and also it is definitely they support the distributed build. So this distributed incrementality is really key for scaling, of course. So every time you change some minimal changes, then you expect minimal build, of course. That's incremental build, as you know. And then, of course, that delta change, the triggers incremental build, but on top of the shared work. Anyone who already did up to this amount of work, then my delta change should be on top of that. That's the implemented by the cached build, by just sharing the artifact of the others' build. And then, of course, you want to have that this delta build must be just done in distributed clusters. So we want to scale with a very large resources, and then we just scale up my build. So that's a remote build. And here, this key to this the incremental distributed build is, of course, the key parameters. Of course, what is the granularity you chose for that cached build? So, in ideal world, basically the module level incrementality, and that means basically cacheability, is very desired. So suppose you have a project, some web app project, which usually have some kind of a very abstract layer of the model of your the internal state, and then handler, and then finally integration layer, app layer, kind of things. Then when some team just decide to develop some new feature, then usually they have to touch the model layer and handler layer and M layer to develop certain new features. And of course, that it's just a single very small change in each model and handler and app, the packages. That just if I have only the package level, the incrementality, then of course that just violates the cache, and then it just triggers the whole build of the model and whole build of the handler and whole build of the app. So that's definitely not desired. So basically why we call module as a module. So module means basically it's a very self-contained unit of the compilation, compilation action. So by definition, we really want to module as a kind of a unit of our incremental build. So then can we do that? So of course, if we have this module level incrementality, then for example, this model has A, B, C, and handler has A prime, B, D, and app has A 2 prime E, something like that. Then once you deconstruct all these dependencies into module level, then you just forget about this model and handler app kind of superfluous the boundaries, and then you just focus on your changes, and A and A prime and 2 prime must be revealed, and then the others are not revealed. So only relevant part is the rebuild. So in this case, basically making this build system know module dependency graph is the most important part, right? So just once they know once the build system knows about the module dependency, then they can optimize the build very incrementally. Okay, yeah. Here the trick is introduced. Basically, in most the distributed build system, including Bezier, usually support only the static dependencies, so-called applicative dependencies. So if you think build as a kind of tool level, so basically build actual level is just your content modifying the operation, right? So this is source code, and A is source code, and then B is the binary, and then it depends on the C and D and something like that. But in build system point of view, build system doesn't see the content of source file and the contents of this generated by binary code. So it just see the A as just file A, and B is file B, file C, file D, and then it just depends on the file A depends on the file C and file D, and the file B binary depends on the binary, something like that. So if this kind of a relation is well preserved, then this is called static dependencies. So as far as we don't need to look into the content of a compilation, then we know build dependency prior to any action execution. That's the static dependency. But in fact, the module graph is not such a kind of things, right? Because module graph is basically, module graph means basically, you have A and B and C modules, and the input header part of the module just depends, lists the dependency. A depends on B, and C depends on B, or something like that. Yeah. So to get the module graph, you have to real action of the parsing, And as a result of parsing, you may end up with some JSON file, for example. And then the basically build system needs to inspect that JSON file, the result of that compilation, and then it just order the next the stage of the compilation, and that's basically the module by module compilation. So at one time, when the module graph is calculated, some dynamic dependency is happening. So that's the tricky part of this module level dependency, module level the incremental build. And very good thing about the Buck2 is Buck2 has the first class support for the dynamic dependencies. So in case of the Bayesian, for example, to have the kind of dynamic dependency, you have to have some kind of pre-process of Bayesian and then so-called Gauger or something, and then it just generated the build file and then do the next action. But it needs another pre-process step. But the Buck2 case, these whole things are just organized and usual, the ordinary dependency step with a certain special mark for the dynamic part. So that is called the dynamic action and the dynamic output, and that is harmoniously integrated in the whole build system. That's the very nice part of the Buck2. And then, of course, we implement, this GHC build group implemented that Haskell rules, Buck2 Haskell rules for the module level incremental build. But to implement this rule, so this is the reason why this group is particularly good for this kind of task. Because, although the Buck2 has a very nice support of the dynamic build, dynamic dependencies, but we should also have some corresponding part of the implementation in GHC side. So this is basically we have to have an expert on this both build system and then also GHC. And of course, the GHC internally, as a usual plain default GHC compilation, GHC make mode, it already does that internally, right? So it has its own the dependency analysis, and internally it has an in-memory data structure out of that module graph data structure, and then it's just that is called downsweep. The dependency analysis called the downsweep, and the upsweep phase it just compiles the module by module in topologically sorted order. So that's what GHC does. Then to adapt this to this incremental Buck2 build, we basically break down these GHC's the internal things to two steps. So of course, GHC already has the dependency analysis step as a kind of separated CLI mode, which is called the MK depends mode. But it actually, until our contribution, actually, it didn't have any sensible output. It's actually its output was a make file, it's a callable format. So we actually implemented this deep JSON API, and then also GHC has the individual module by module compilation using the so-called one-shot mode, which is basically -c the compilation flag. So, but of course, for that we have also some kind of performance optimization, and also we need to implement some the certain features, so-called prefer byte code feature for the one-shot mode. So kind of for this purpose, we also need to a lot of the implementation, some the improvement in the GHC is needed. So once this is done, then now all the nicety from the Buck2 is just automatically coming. So it is managed by Buck2, then all is suddenly remotable. So as you know, if I just write down some project like this Haskell library, the Buck file, and then it break down this dependency analysis step, and then each the one-shot mode compilation step like this. And then those, each step generated these artifacts. But all these artifacts generation, the compilation action can be just remoted, can be just sent to the remote server, and in the remote build executor instances, and then all the results out of that action will go to the content of the server store, and then later it can be just fetched from the later users. So this is just implemented. I mean, as a bonus. I mean, as just a default implementation of Buck2. So, and again, this is already very nice result, but we also want to optimize this further. So, as you know that when we fine-grained this whole GHC make mode, we just deconstructed this GHC make mode. Then this deconstruction actually allows us to do a lot of more aggressive optimization. because as you already break down all these the build steps in module level, then basically this package boundary is arbitrary, and then in previous case with the package boundary, for example, module decompilation is waiting for the whole this model package compilation ends. But if you see that the module level, the dependency, the D doesn't have to wait the end of the compilation of the A. So we can actually obtain the more parallelism in the compilations. So this is what we call the cross-package parallelism, and this is very doable. So only the package level dependency is the relevant part is only the last artifact of this model and handler and app. In this case, the dynamic library. So only that part is depending on each other, but the other part, all this one-shot mode, the module level compilation should be just equally parallelizable by that as the module graph allows. So that is very important to the optimization we want to add. And actually, this is a little bit tricky. The reason why is basically, although the module level it depends on only the other modules, but in fact it depends also the some configuration package configuration file in the GHC's CLI parameters, which is in the right. But the package.conf has the information about all the interface files, but also it has an information about the library file. Because of that, the package.conf is depending on the library of this the dependency packages. So to really implement that cross-package parallelism, we had to break down this package conf in two stages. So one is the before the actually final stage, and then the other is the final stage. And basically, the module level, the dependency analysis, and then the module level compilation should depend only on the stage 0, and then the final library installation depends on the stage 1, in the sense. So in a sense, this staged package pass around, and then the package, the information has some kind of mutable state. So it's a very similar to kind of a laziness in a sense. It's a kind of it has a thunk state. So somehow this library is thunk, and as when the final evaluation is done, then this library is finally evaluated in a sense. So this is basically some kind of a form of the continuation or some form of the future. So this is basically the new things we actually introduced this Buck2. Actually, this is the Andreas' work, in fact. So we introduced the dynamic value. So dynamic value is basically the implementation of the continuation in this Buck2, the build graph. So ordinarily, the Buck2 dynamic action, dynamic output, you can think that as a kind of state monad. So every time you have this kind of dynamic action, you have some state monad, the state threading. But if you have the dynamic value, then it has a kind of it's on top of that state monad. You have some continuation monad. So you just give it some kind of a future implementation. Yeah. Okay. So then, of course, the Buck2 controls this execution of the dynamic actions on-demand basis. Okay. So after this cross-package parallelism is done, so say this is a model and this is a handler and then this app. Then previously this handler was waiting for the whole this model the package ends, and then of course this app waiting for the handler part ends. But after that, it's just a mixture of all this kind of module compilation. So it's much faster. So we have we reached quite a big performance boost of that. Yeah. Oh, go ahead.
Just go back one slide. The purple line is longer than the
I think that it's just this scales. Yeah. So.
I'm just wondering, what's the net reduction or the total wall time from one to the left?
I don't remember about this example, but Andreas, do you remember?
On this, I mean, right here.
Yeah.
Oh, yeah.
So what is the real the number of for the reduction, total time reduction?
I mean, right there, it seems to be a third on that scale, but in total, I don't remember.
Yeah. Okay. So this is a 6.4 and this is 4.2. Yeah. So 50% reduction. Yeah.
There was a talk at last year's HIW where presented some data with the Amazonka package. I don't remember the numbers by heart, but it's pretty, so you can look at the recording. The numbers are in there.
It depends on the workflow, a lot with Hugo. Like on Hagen, it's like 20% better doing this. They provide GH factors.
Since you do compilation at module level, not package level, do you actually use Cabal at all?
We don't use a Cabal at all. That is actually the very important point. So we basically, this Buck2 build system, we basically bypass all this Cabal layer. So basically, this the Haskell library directly uses a GHC and GHC package. Yeah. So in a sense, it's another Cabal. Yeah. Yeah. Go ahead.
But is the package description Cabal? So you convert from Cabal files to your custom format, or do engineers write their own package descriptions for the boxes?
Yeah, so the question is whether the package description is different from the Cabal or not. Yeah, so actually very similar to Cabal in a sense, because Cabal is just modules and then also GHC flags and also the dependencies. So fundamentally it's the same. Yeah, but it's more the low level in a sense because it's more have more control on these GHC options because it's directly controlling the GHC options. Yeah. So. Oh.
When are we going to get a Buck2 build for GHC itself?
Hmm?
Can you apply this to the GHC build?
Oh yeah, actually one of my pet project is actually using the Buck2 for the GHC build, and then actually probably in this GREAC I will work on that. Yeah.
With such small units of compilation, don't you lose in round trips to the cache what you gain in parallelism?
Yeah, definitely. So there must. I mean, this is if you just the question is whether what is the I mean, if especially the build is short, then whether the cache is really beneficial or not. So Buck2 has first of all the hybrid mode. So you can actually. I mean, this is only remote execution. But yeah, anyway, you can actually choose the faster part, faster things than the slow things. So dynamically. That's one thing, and also, usually I think at for the big project, the cache gain is much bigger than the usual. So actually, I'm showing the actual number in my Mercury project. Yeah.
I looked up the Amazonka numbers if you want to share them. So this is an end-to-end Amazonka build comparing local Cabal, local Buck2, and remote Buck2.
Yeah. So for example, for the Amazonka build, the local Cabal takes 1 hour and 6 minutes. But the local Buck2 takes 2 hours and 3 minutes because of some overhead I will talk about. But if you use the remote build with 100 cores, then it took 15 minutes. So as you have more machines, then you can have a much faster build. Yeah.
Yeah. So if I have a project, say multi-package project that I build with Cabal, how difficult is it to migrate that to Buck2, and can I actually use both? I mean,
yep.
So that I don't not.
Yeah. So the question is how difficult to migrate the Cabal project to Buck2, and then how difficult? Yeah, that's fairly easy actually, and then can use both. So and then in fact in Mercury we actually have both Cabal build and then the Buck2 build, and our build is fairly complex in terms of the Cabal. So yeah, so it's fairly doable. Yeah. So
Is that automated or?
It's not automated yet. There is no Cabal to Buck or like a Cabal to Nix. But I think even you can make that kind of tools. It's not very one-to-one. Anyway, the Buck2 the rule is really literally GHC invocation. If you look at then so it's you can easily make that kind of analogy between the GHC and the Buck2. Yeah.
So just to follow up to that, I mean, ideally you would teach Buck2 to just consume Cabal files, right?
Yeah. So that's also possible. Yeah. Yeah. You can make the Buck2 work with the Cabal directly. Yeah.
Did you at any point look into how difficult it would be to teach Cabal to do cross-package parallelism, or were you just like, there's no point?
Yeah. So for us, the question is whether this is the more benefit than the Cabal cross-package parallelism or not. That's basically or.
I was just wondering if you do that as well, right? Like clearly you won't get remote builds from Cabal, but
Yep.
you said you already also have a Cabal build, so getting cross-package parallelism for Cabal would benefit you and lots of other people.
Yeah, I think even the cross-package parallelism in Cabal, there is not this module level the cross-package parallel. So if Cabal depends, I mean, if two Cabal project does not depend on each other, then it can be parallelized in that multi-package build. But if it really depends, then it's not really the module level the parallelism. Yeah, I think.
Cabal uses make mode, so I think that precludes a lot.
Yeah. Yeah. So the last question and then
Just one brief comment on the question about converting from Cabal to Buck2. So my colleague Andrea Bedini has been looking into this kind of thing as well to sort of parse the Cabal file and generate Buck2 definition. So that's definitely doable, just as a brief comment.
Yeah, good. Thank you. Okay, since I have a little time, so I'm going fast. Okay, so still actually, as you see, the Cabal build is still for the local build, as for the Amazon car project, is twice faster than the Buck2 build. The reason why is basically the intrinsic the overhead from this one-shot mode calling. So first of all, because now GHC maker mode is just one process, build everything. But the one-shot mode, this Buck2 uses one-shot mode, and then every module has a separate process. And then GHC itself is fairly big binary, so it is a heavy program to start, first of all. And then if your project uses template Haskell, then it resulting in each template Haskell splashing resulting in loading the dynamic library and the bytecode object in each GHC process. And it actually gets only worse in downstream modules because the template Haskell transitively depends on all these modules. Actually, this is exactly why we invested in this, the explicit level import. Okay? So this is, the explicit import is also one of the outcome of this the effort. But this is one way of solving this problem, right? So just the template Haskell depends on the other dependencies very minimally, so that we just minimize the loading time and loading the resource overhead. However, anyway, if that kind of the initialization overhead exists, then we need to solve the problem more fundamentally. Then the solution is basically GHC as a server solution. So as you know, so basically it's a revival of some GHC make mode in a sense. So although the Buck2 itself just treats every build process as a separate process, but it just, if you use the persistent worker, then it just uses the gRPC protocol, and then it communicates with the GHC server daemon in a sense. And then in this case, the proxy daemon exists, and then it just creates each server instances for certain, the group of targets. And then basically it keeps just send the request, and then this GHC server just has a persistent state and then updating its state the request by request. So in our current implementation, we just recycle the loader and then name and symbol cache states from the GHC and from the early module compilation. So in this the implementation, currently we converted the Mercury code base 2,000 modules right now. And it already gives us 3 times the performance improvement. So 27-minute build goes down to 9-minute build. And then, as I said, as we go downstream, it's more template Haskell, burden is more bigger. So this factor just will go up. So this persistent worker is really, really important to the optimization. So, okay. So by the way, this persistent worker, this GHC as a server, it doesn't not only used for this kind of build acceleration for the Buck2 build system, right? So it can be used for the backend implementation of the language server or some. So as we mature, we can maturize it. We can standardize the API, and then it can be used for the part of the GCC feature. Of course, not the gRPC part, but just some API part of the server communication. Yeah. Okay. But then with this new system, basically we do quite radical things about the GCC pipeline, in fact. So we already deconstructed GCC maker mode, and then we even just specify specific target artifact and generate it early. And then only the minimal dependency, if the prior dependency is not calculated, not the build, then only the minimal dependencies can be built. So for example, I can just get the dependency graph only, or I can just generate only the dynamic object from this D module, or I can generate the interface file of the D module, or even by some, our work, we implemented this incremental header in GCC. So even the one specific HTML file from the certain module can be generated. So it is very, 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 very flexible. Yeah. So I feel like this, next target, this is a little future task, but some of the part is already done. So for example, we can consider this first class byte code object as just the artifact from this GCC build, and then use it as a separated target, and then it can be used for the we don't just generate all this kind of object file, but only the byte code object from that the optimized build, and we can use that as a kind of the fast loading the GCCI sessions, especially with the multi-home unit support, or the GCC debugger. So this has a lot of potentials. And that means basically we can have a very fast type check only target with template Haskell, and then also fast type aware indexing is also possible. So, and also we want to make some kind of intermediate state which can be shared with the profiling and then just the non-profiling things. And if it is possible, then we can even unify the build. So now the profiling build is just a duplicated build, alongside the ordinary build. But can we just optimize that further? That's also my interest. Yeah. Okay. So like almost the last thing. So does it work well? That's also the many people may ask. Yeah. Yes. We are still. I mean, in the middle. Just right now, we are in the middle of the migration yet. So not whole the 14,000 modules are not yet converted. Actually, in work in progress branch, we already converted it, but for the CI now finally we didn't. CI, which is always committed every day in master, we didn't yet. But yeah, it actually shows already the cache hits with enormous, and for those converted from our actual numbers, almost more than 90% of our CI build are just pure download. So it's just saving our time a lot. And then even if build occurs, still it's a very small partial build. And if you count only the built modules, then only 99% of module level builds are just cached. So it's a very rare to hit the real full rebuild. So this is a really, really the good big benefit for the scaling. Okay, so the conclusion is just what I'm summarizing what I'm saying. Yeah, thank you.
Thanks. Maybe one question? No? Yes? Michael?
Did you look at splitting up interface files? I think somewhere on the GHGC tracker there's an issue about splitting up interface files so that you can start type checking the next module sooner. So I think at the moment we do more work than we need to before we're then willing to start type checking the next module. So maybe I make that up. There's something about that. Maybe
Yeah. Okay.
Okay. Well, I think let's thank the speaker again.